Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So this is another video from the Strivers A to Z DSA course. Just in case you're for the first time here, this is world's most in-depth course in DS Algo. Why do I say that? This course alone has 456 modules. When we end the course, we would have solved over 400 plus problems. You can go over the entire internet. You can buy any of the paid courses. None of them will be covering DS Algo in such depth. So one thing that I can give you as a guarantee is if you complete this course, you can actually clear DS Algo rounds of any of the companies in any portion of the world. So till now we have covered till step 3.1 this problem. Now in this video, we will be covering the remaining two problems from step 3.1. So to start off, let's get started with the first problem, that is longest subarray with given sum. And it just has positives in the array. What does the problem state? Find me the longest subarray with a summation of k. So the first question that might be coming up to your mind is, but what is the meaning of subarray? We haven't heard about this before. So just keep this in your mind. When I say subarray, it means contiguous, very, very important word. Contiguous part of the array. Contiguous part of the array. So I can say that this in itself is an array of 1. So that's a subarray, a part of the array. I can say this is 1, 1, 1. So it's a contiguous part inside the array. So it is called a subarray. I can say 4 to 3 is a subarray. I can say 1, 2, 3 is a subarray. What I cannot say is 1, 2. I cannot say when I take 1 from here, when I take 2 from here, I cannot say it's a subarray. But if I take 1 from here, if I take 2 from here, that's a subarray. So a subarray has to be taken from contiguous portions. Otherwise, it is not a subarray. Imagine if you take like 1, 4, 3. Yeah, you have taken 2 people who are consecutive. But then the other guy is not. So this is not a subarray. Rather, this is a subsequence. So I hope you've understood the definition of subarray. Now what they are asking you is, find me the longest, very important, find me the longest subarray who has a sum of k. So can I say, if I take these two elements, they will have a sum of 3. They will. And what is the length of this subarray? 2. If I take just this one, this is also subarray. And the summation is also 3. Right? Because that is what they are looking for. And the summation is also 3. But the length of the subarray is 1. And what they are asking is, give me the longest now. Give me the longest. So if I take this, the summation is 3. And the length is 3 as well. The summation matches. And the length is the longest. You cannot have a longer length than 3. Yeah, this is also a subarray with length 3. So there are 2. But they are not asking you the count. That problem we will do in the future. But as of now, they're not asking you about the count. What they're asking you is, give me the length of the longest. So what I can say is, the length of the longest over here is 3. And that is what they're asking you to return. So this question comes up in an interview. What is the first solution that you'll give to the interviewer? Obviously the brute force solution. What is the brute force solution? It's very simple. I'll say, hey, I'm going to generate all the subarrays. Yes. That's the most obvious thing that comes to your head. Generate all the subarrays. And I pick up one by one, and I find everyone's sum. I generate every subarray, and I find everyone's sum. And whoever is the longest, that's my answer. So that's the obvious brute force, like the most simplest approach that can come to my mind. But the question arises, how do you generate all the subarrays? So we need to observe a pattern. Can I say 1 is a subarray? I can. Can I say 1, 2 is a subarray? I can. Can I say 1, 2, 3 is a subarray? I can. Can I say 1, 2, 3, 1 is a subarray? I can. Can I say 1, 2, 3, 1, 1 is a subarray? Do you see a pattern? Yes, you do. It's extending by 1. It's extending by 1 every time. And it goes on till the last. And each of them is a subarray. Starting from here and ending at all these indexes. Very obvious. The next pattern. Can I say this is a subarray? Yes. Can I say this as a subarray? Yes. Can I say this as a subarray? I'll say yes. Can I say this as a subarray? I'll say yes. Can I say this as a subarray? I'll say yes. Can I say this as a subarray? I will say yes. This. Again, can I say 3 as a subarray? 3 1 as a subarray? 3 1 1, 3 1 1, 3 4 1s, 3 1 1 1 4. This. Yes. Can I say this as a subarray? Yes. So do I see a pattern? I do. Every time, if I keep a pointer I here, then I can just take a pointer j. And the j will always start from I. And then what I can do is, I can say the subarray is from I to j. Do you see the first time? J is here, I is here. So the subarray is here. Then what I do is, I move j. Can I say the subarray is from I to j now? Yes. And then again I move j. And can I say the subarray is from I to j? And then again I move j. Then again I move j. And I keep on moving till it reaches last. If it reaches last, the entire array is a subarray. By the way, an entire array is also a subarray. So, fine. I can move j. Next, once j has reached the end, what do? You move I. And now can I say, j this time again starts from exactly I. Because this is a subarray. And then again you do the same thing. Move j. That's what you do. And eventually this is subarray, then this. So I and j keeps on moving. So something I know for sure is, I'll keep I and I'll keep j as moving. So let's write that. So can I say I can write this as, for I equal to 0, I lesser than n. Why I lesser than n? Because first time I was here, then I will be here, then I will be here, then I is here. Eventually it will go till the end. Right? Where does j start in from? When I is here, j starts from here and goes till the end. So can I say the inner loop will be very simple. J starts in from I and j goes on till n, j plus plus. This is how it will look if I have to generate all the subarrays. And where is the subarray from? I to j. Where is the subarray from? I to j. Is it? Because if j is here, I is here. Can I say the subarray is this? How do you find the summation of this subarray? It's easy. If the subarray is from I to j, run a loop na. Run a loop. So I'll say, okay, k is equal to I and it can run till j. And the summation can be 0. And summation plus equal to array of k. In this way, I can summate the entire subarray from I to j. In this way, I can summate the entire subarray from I to j. Now, what was required? Longest equivalent to k. So, equivalent to k. Okay, let's write that condition. If s is equivalent to k, then the length, and maybe you can keep the longest length as 0. So, the length will be max of the previous length, comma, what is the length between I and j? What is the length between I and j? Imagine I is here and j is here. What's the length? 2. So that's j minus I plus 1. That's j minus I plus 1. Very simple maths. J minus I plus 1. And eventually, wherever there is an equality, we take the longest. And right at the end, we can print the answer as length. Done. What is the time complexity? 3 loops, somewhere near about big O of n cube. Near about, not exactly. Why? Because this loop is diminishing. This also will reduce. So I can say somewhere around n cube. Not exactly. Am I using any space? The answer to that is no. We are not using any extra space. So we have kind of understood the brute force, which is n cube. But the interviewer will say you, hey, wait. Do you actually need n cube for the brute? Can you optimize your brute? I'll be like, maybe yes. I'll say, wait. I'll probably remove this and try to figure out an observation. Can I figure out an observation? And the observation is going to be very simple. See. Where is the first subarray? And then what is happening? The first time, the summation of the first subarray is 2. Then the summation becomes 5. Then the summation becomes 6. Then the summation becomes 1. What is being done to the sum? First 2 was added. Then in the next subarray, we know the summation will be 2. Only one new element came up. So just add the one new element now. Then again one new element come up. So add the one new element now. And again one new element come up. Add the one new element na, and get the summation 7. Do I need to iterate in the entire subarray? We do not. Because when the j is moving, I just keep on adding. Quite simple. So what I'll say is, let's keep the S as 0, and every time j moves, I'll just add it. What will be the value for the first time? If I is here, first time 2 will be added, then j will move here, then 3 will be added, then j will move here, 1 will be added, and eventually everything will be in S, and you can easily compare. So if I do this, the brute force boils down to somewhere near about n square with a space complexity of big O of 1. So this is what you'll tell the interviewer, that the brute force that I can do is big O of n square at the best case. So obviously the interviewer will not be happy with the brute force solution, and he'll ask you to optimize it. And that's when you will come up with the better solution. And the better solution is going to use hashing. So what is the thought process behind hashing? Let's understand that. So what I'll write is, I'll just write dots. I'll not assign them any numbers because I don't want you to just think it in terms of an example. I want you to think it in a very general perspective. So this is an array with random numbers. And what am I looking for? I'm looking for any subarray with a sum k. That's what I'm looking for. Okay, so we will do some reverse mathematics. Imagine you are standing here. Just imagine you are standing here. How many elements are from the front? 5. So imagine I can call it as prefix sum. What does prefix sum means? From the front till that portion. Prefix. Got it? So prefix sum is assume some x. So what am I saying is the complete sum is x. Okay. Now my very simple question to you is, this is the last element. How many subarrays will be there who will have the last element as this dot? You'll be like, okay, one subarray is this, who will have this dot as the last element. The other one is this, who will have the dot element as the last. The other one is this, who will have the dot element as the last. The other one is this, will have the dot element as the last. The other one is this, will have the dot element as last. Can I say this? No, because the dot element is not there. I need the dot element to be the last. I cannot even say this because the dot element is not the last. Only there are 5 subarrays. One is this, the other 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 one is this. There are 5 subarrays with the dot element as the last, and that's what my focus will be. Okay. So can I say, if there exists, I'll write this. If there exists a subarray with summation k as dot as the last element. Dot as the last element. So hypothetically imagine these 3 numbers give you the summation of k. Hypothetical. Probably there exists a subarray who has a summation of k. But you cannot have this sum of some middle subarray in between. But can you do reverse engineering? And can I say, wait, probably there is a subarray. Probably there is a subarray with a summation of k. So if there is a summation of k, what will be the summation of this? Reverse mathematics. If the entire is x, if this is k, can I say this will be x minus k? X minus k. I can. This is what I will use. Can I say, if I'm standing here and till here the sum is x, and if anywhere previously I got a sum x minus k, if anywhere previously I got a sum x minus k, can I say this? That this will be k, this will be k, this will be k. I can. I just did reverse mathematics. I cannot find the middle sum. I cannot find the middle sum out of nowhere. So I did a reverse mathematics. I said, I can carry the sum till here and that will be x. I would have carried the sum till here as well, which is x minus k. So if over here standing it is x, if at previous there is someone with x minus k, that means I have a mid subarray with k. I got some subarray at k, and I can do that with every element. I can do that with every element as the last element. Hence, proven that I can generate all the subarrays. Understood? Probably a bit, probably not, probably completely. Doesn't matter. Let's get back to the dry run. It'll get to your head directly. So let's do the dry run so that this concept gets into your head. So what I'll do is I will take an hash map. Okay. Why will I take this hash map? Getting back to this thought process. If till here it is x, I just want to see if previously there was x minus k. You cannot see out of the blue. You cannot see out of the blue. So what you have to do is you have to kind of hash it. Till here the sum was x minus k. You have to hash this. So that's the thought process. Did not understand? Not an issue. Let's do the dry run. So we will be at the first element and we'll do a summation 0. And initially no subarrays are found, so length 0. First element 1. Increase the summation to 1. The summation is 1. And that's not equivalent to 3. So you take 1 and you say it occurred at index 0. Probably I'll write the index for better understanding. So 1 occurred at index 0. Done. Next, move the pointer. 2. Summation increases to 3. Summation increases to 3. Which is equivalent to k. Which is equivalent to k. So what you say is, okay, wait. This entire prefix sum is equivalent to the k. That means this in itself is an array or a subarray who is giving me this sum. So if the subarray is till index 1, so the length will be 2. 0 based indexing, so the length will be 2. Perfect. And at the same time, say you got 3 till here, which is index 1. Perfect. Let's move. You got 3 now. You got 3. The summation will be 6. The prefix summation is 6. The prefix summation is 6. Now comes the twist. So 3 elements. And till now the prefix sum is 6. And you're looking for someone with 3. And that someone is this. So if this is 3, I did a reverse engineering. The remaining was 3. I said, hey, wait, did we get some 3 before? And he says, yes, till index 1 you got a 3. So that means this subarray, there does exist a subarray with a k. Reverse. So what I'll do is, I'll say, till here it is 6 now. You need 3 now. 6 minus 3 is 3 now. Look from the front. Is there a 3? He says, till 1 there is 3. Till 1 there is a 3. So I'm getting a subarray. You're standing at 2. Till 1 there is a 3. So 2 minus 1. So the length of that subarray is 1. The length of that subarray is 1. But that's not greater than 2, so you'll not do anything. So 6, 2. Perfect. Let's go. You got 1. 7 is the new sum. So what can I say? I have 4 elements. And the prefix sum of this is 7. What am I looking for? 3. For someone to be 3, someone from the start has to be 4. Do we have someone from the start as 4? No. So did not find. Take the 7 and put it at index, how much is that? 3. Perfect. And now let's move. So when you move ahead, you get 8. So when you're getting 8, which means you're having 5 elements. And again, right, you're having 5 elements. It is having 8. So for someone to be 3, someone has to be 5. Is there someone with 5? No. So just put 8, 4 and move. Next, you move ahead. So that's 9. So there are now 6 elements. 6 elements are giving a summation of 9. 6 elements are giving you a summation. So for someone to be 3, someone has to be 6. And I get a 6. I get a 6 at index 2. So this is 6. So these many remaining will be 3. So you're currently at 5. Till 2 there was 3. So the subtraction, the length is 3. So you got a better one. So this is how you can go ahead and you can figure out if someone was there in the back. This is what I will call as a better solution. So I hope you've understood the thought process and the dry run. I'll be coding this up because I want your coding skills to go up because this is a very important question. So you're given the vector and you're given the k. Something important to notice is it is given as long. First declare the map. So map will be long because that is where we will store the prefix sum. So you can say pre-sum map or something like this. Perfect, done. Now what I'll do is I'll go across the entire array, which is something like a.size. So let's go across the entire array. Now what I'll do is I'll declare a sum, and again please take long. And over here I'll also take a length as 0. At the end of the day, I can say return length, or this can be max length to have better naming. So I can take max length. Perfect. Over here, I'll say sum plus equal to a of I. And remember, initially always check if the array from start till the current index is giving you k. If it is giving you, then the max length will always be max of max length comma I plus 1. It will always be like, even if you do not write max, it will work, because if you add I, that's always the maximum. Okay, if that's the case, that's perfect. What can be the other case? I'm looking for remaining. Bring the reverse mathematics. How much do I require? This is what I require. So if my map has this remaining, which means it will not be pointing to the end. So remember, this is pre-sum map. So please write pre-sum map dot end. If it does exist, there means it does. So thereby, what will be the length of this subarray? Can I say the length of this will be I minus pre-sum map of the remaining wherever it is. And then you can do a same max length equal to max length, comma, length. Right at the end of the day, whatever sum you have generated, you say pre-sum map. Yes, you say pre-sum map of this particular sum is equal to I. Something to ponder over here, like this, if I try to submit this, this will run. There's a slight edge case that I want to talk about. This code that we have written, is that correct? That is correct, but only for positives. If I tell you that the array has zeros, the code that we have written will be wrong. Why? Let's understand that by an example. So imagine I take an array which has something like 2, 0, 0, 3. And I'm looking for a summation of 3. That's what I'm looking for. How does it work? It's very simple. We take a prefix sum, we keep a pointer here, we have a hash map, right? And then we have a length as 0 initially and prefix sum as 0. Let's start the iteration. When we are at 2, which is index 0, we do the prefix sum as 2. And we say, this is 2, is that equivalent to this? That's not. And we know one element is 2, so is there any one previous? No, so that's fine. And then we go across and say in the hash map, 2 occurs at index 0. Done. Next we move. How much is it? 0. So 2 plus 0 will still be 2. So till here we have 2 again. And that's not equivalent to 3. And 2 elements are having 2, which is this. So for this to have 3, someone has to have minus 1, which is not possible, right? So, okay, fine. But till here, it is again having 2. So the hash map this time replaces to 2, 1. Then we move. Again 0, 2 plus 0. Again 2. Hash map this time represents to 2, 2. So let's erase this. It will be 2, 2. Done. Next when I go here, it becomes 5. And it's like 4 elements are having 5, which is not 3. How much am I looking for? I'm looking for 3. So I need someone with a sum 2. And when I look at the hash map, it says till here the summation is 2, which is correct. So thereby, this much is the subarray, which is again correct. But we need longest. We do not need shortest. We need longest. So apparently, we should have just stored 2 for index 0. And this subarray 0, 0, 3 would have been the answer for longest. Thereby, if a sum previously does exist, you should not re-update. Because if there is something like this, and this one has a summation of x, and you're looking for k, you'll try to look as left as possible for x minus k. You'll try to look as left as possible for x minus k. Did you get this? I hope you did get this. Because you'll try to look for the leftmost guy for the sum of 2. Because sum of 2 is here, here and here. But you take the leftmost so that you get the longest subarray. This is where it will fail. So there is a slight change in the code that you have to do. So if I go back to the code, this line will be inside braces. And if you're putting that into the map, what will you write? You will say okay, wait, what's the map's name? This dot find, was the sum previously not there? If it was not there previously, then I will go ahead and say, okay, cool, that was not there, so I'll just put it. So it's a minor change, by the way. Looks like, okay, sorry, my bad. Okay, should be good. And let's just format this. Okay, perfect. Now let's quickly run this and see if it is running fine. So what did I say? If it does exist, I will not. And now I will go and submit this, and this will be running. Oh, it did not. Why? Also, you've got to change this to long, and now you can go ahead and submit this. This should be running fine. Yeah, it does. So I hope you've understood how do we cover the edge case. And the same code will also run if it has negatives. Because in the negative, we apply the same logic and it does run. But if you observe, this particular code is partially accepted. Why? Because this was the better solution that we were discussing. We still need to optimize this. But this same code will work for a problem that has positives and negatives in the array. Because in that case, the better one for the positive and zeros is the optimal. You cannot optimize this code any further if the array has negatives, zeros, and positives. So I'll just quickly go and submit this, and you'll see that this is actually, okay, so just change the name now. Okay, cool. So you'll see that this is actually running for this particular problem, and it will be completely accepted, yes. While over here, it was not, because this is a better solution. So let's discuss the time complexity and see if we can get an optimal or not. So we did code up the better solution, and if you saw that, that better was an optimal one if the array has positives as well as negatives. But if I ask you for the better solution, yes, what is the time complexity? I can say I'm definitely iterating in the array, and we're using a hash map to find and initialize in the hash map. So it can be logarithmic of n if we are using ordered map in C++, or else it will be n into big O of 1 if you're using unordered map. But again, unordered map, if it goes to the worst case, like the constraints are in such a way that it ends up having a lot of collisions, then this one, that big O of 1 search time in the map, ends up being big O of n. Hence, the worst case can be n square if you use unordered map. So tell that to the interviewer that I can use unordered map. If I do not have collisions, I'll end up having n cross 1, which is big O of n. And I will have n logarithmic of n. If I'm using ordered map, it will not have any collisions. What will be the space complexity? The space complexity will be, we're using a hash map where we are storing every prefix sum. So the worst case, every index will have an individual prefix sum. So thereby a big O of n, because all the prefix sum are stored. So this will be the time complexity and the space complexity for the better solution, and for the optimal in case the array has positives and negatives. Whenever you're telling the solution in an interview, make sure that you tell them about the better solution and then explain the edge case about 0 and the negatives, and then tell them descriptively that that will only work for, like, that will be the optimal solution for positives and negatives. But if the array just contains positives and zeros, I will turn to the most optimal solution that will be using the two-pointer approach. It will be like a two-pointer and a greedy approach. Very simple. Let's start off. So the thought process is something like this. Before moving on to the dry run, let me tell you the thought process. It's something like this. We have a single point. Then we keep increasing. So the moment we move right in the array, the summation is bound to increase. And there will be a point where it will go beyond the sum that I'm looking for. If it will go beyond the sum, I'll not move here. Rather, I'll try to trim it down. I'll try to trim. And then it will just be this. It's like, go. If it increases, trim from the left. Go, trim from the left. Go, trim from the left. Go, trim from the left. That's what we will do. That's the thought process. If you did not understand the thought process, not an issue. Look at the dry run. You'll understand it clearly. Let's go to the dry run. So what I'll do is, I'll have a pointer here. I'll have a pointer here. And I'll keep the summation initially. So what does the pointer means? It means the subarray that we are considering is just having 1. So the summation will be that element itself. The summation will be that element itself. Remember, we are looking for a summation of 6. And the maximum length subarray till now is 0. Move. So as of now, the summation is 1, which is lesser than 6. Doesn't matter. Let's move. We have 2. So add up 2. We get 3. So this is the subarray. 3 is still lesser. Fine. Move. We get 3 again. 6. 6 is equal to 6. If it is equal, fine. From here to here is the subarray. And you can easily find the length by subtracting this minus this. And the length will be 3. Quite simple. Next, move. How much is that? 1. Add it up. 7. Now the next time, when you try to move, before moving, you say, wait. I know I need to move. But before moving, the summation is 7, which is greater. Why will you move? If you move, the summation will further increase. Wait, let me reduce it a bit. Then you will move. Let me reduce. I'll be like, take out 1. So if you take out 1, it will be back to 6. If you take out 1, you'll come over here. So I'll just erase this so that it's cleared. I'll just erase this. And now I'm like, okay, wait. What's the sum now? 6. Okay. Equivalent? Now let's do it. I'm like, okay, one more subarray equivalent to 6. What's the length? 3. Fine. Not an issue. Now let's move. Again 7. In the next step, when you try to move, you're like, 7. Wait. You have exceeded. Let me shrink. So I'll now remove 2. The moment I remove 2, it becomes 5. So remove 2. It does become 5. Next, I'll try to move now. This. If I try to move, I'll again get 6. I'll again get 6. And now I'll be like, okay, full length. Fine. Update the length. Next, if I try to move this to here, this will be taken. It will again exceed. So the next step, before moving this, every time before you move, you'll see the sum. It's more. Shrink. Summation will be reduced to 4 because 3 has been omitted. 3 has been omitted. Perfect. Now let's move. 3 is added. What's happening? Again 7 went up. That's a lot of number. So, cool. Done. Next. When you try to move, you will not. Why? Because you still have to shrink. Let's shrink. 1 taken off. 6 again. Now you'll move. We have 3. Add it up. 9. So when I'm at here, this 3 is added. The next step, before you try to move, you'll be like, wait, sum is 9, which is greater. Remove sum from back. Remove from back. Then you will move. I'll be like, okay, remove this one. So if I remove this one, I'll move ahead. It'll be 8. Okay, remove this one. Move ahead. It'll be 7. Okay, remove this one. Move ahead. 6. Now, you'll be like, okay, this is equivalent. One more guy. But this is length 2. Not to be considered. Next time, you move. Done and dusted. So apparently, I got 3 subarrays or 4 subarrays. And we got the maximum as 4. And the moment it exceeds, you stop. Got it? Very simple. It's a 2-pointer. Move, exceeds, move. Again move, exceeds, move. Move, exceeds, move. Quite simple. Okay, so let's quickly go into the compiler and try to code this up. If you want to try this problem, the link will be in the description. So, we were having a left pointer as 0 and a right pointer as 0. And we were having a long sum. So, initially, what's the subarray? Is the single element. So, sum will be array of 0. Perfect. And we know one thing, rather max, int will do. Max length is equal to 0. And int n equal to a dot size. Okay, perfect. What were we doing? We were moving right. Till it doesn't crosses the boundary. Quite obvious. Till it doesn't crosses the boundary. What else I was doing? Think on yourself. What else I was doing? I was like, okay, I know one thing for sure. If I'm moving right, I'll have to add someone. I'll have to add someone. But if you go back to the iPad, initially you were here. Summation was 1. Then you added the next guy. So you have to go to the next and then you have to add the 2. To go to the next, then you have to add the 2. So, can I say, first I'll move. Then I will add. Very obvious. First I move to the next, then I add. But before adding, I need to be sure. I need to be sure about one thing. Am I still under the boundary? Am I still under the boundary? Because what if I'm standing at here and I move to the next and I try to add and it's not there? So we need to be careful. Only if it's inside the boundary, then add. But can we do this always? That's my question. Can we do this always? It's like, I don't think we can do that always. We can only do that if a summation is somewhere still inside the boundary. Agreed? But for that, can I say, while summation is greater than, if the sum exceeds the k that you're looking for, then it's very easy. Just subtract what the left guy and move the left. Is it that tough? What am I saying? If it's more, from the left, keep on subtracting. Quite easy. And keep on subtracting and move the left. There will be a point when summation will exceed k. That's it. That's what you have to do. And probably you can just write one more thing. Till left is right. Which means till there is a subarray. This means left, there is a subarray. If left crosses, there's no point in, like, because if you've taken till here, you can only go till here and subtract these guys. That's what I'm doing. This is as easy as it gets. But before adding, this is the moment you have subtracted. This is where you check, okay, I've subtracted. Now, assume this is equal to k because I've subtracted everything which is greater. Assume after this it's equal to k. If it is, I say max length is equal to max of max length, comma, what thing on this? I'm at left and right. So it's like right minus left, is it? Plus 1, yes. And then over here, you can go ahead and return max length. Quite simple. Let's quickly run this and see if it's running fine. It is. Let's quickly submit this and see if all the test cases do pass or not. This time, not really, and it is giving us a correct answer. So what I can say is, this is an optimal solution if the array contains positive and zeros. But if negative, then this is the optimal one. You cannot optimize this. Okay, so what is the time complexity? On the naked eye, it might look like 2 while loops might be big O of n square, but that is not the case. The time complexity at the worst case is big O of 2n. Why? Let's analyze. So, can I say the outer while loop is the right pointer running till n? Can I say this? I can. So if the right pointer is somewhere here, it runs till here, which is a big O of n in itself. Now you might argue, inside this there's a while loop. Inside this there's a while loop. And this is running for big O of n. But is this always running for n? N. If this while was always running for n, then this would have been a big O of n, then it would have been a big O of n square. Can I say this while loop is actually running for, maybe for the first time it ran for once, for the next time for twice, for next time thrice, for next time once, for next time twice. So overall, in the entire iteration, it will run for a big O of n, but that's overall. So it might happen, first time when the right pointer moved, the while did not run. So it's like 0 iterations of while. Next time when the while right moved, there was again 0. Next time when the right moved, the while was 0. Next time when the while moved, it was 0. Next time when it moved, maybe then it took 3 iterations. So it's like 1 iteration, 2, 3, 4, 5. 3 means 8. So it's like 3 got added to the number of iterations. Got it? 3 got added to the number of iterations. Next time the right might have moved. Then the right might have moved. And then again maybe 2 iterations was done. So it's something like this will be n. This will be big O of n. And this will be in itself big O of n. It's like n plus n. Thereby the time complexity is big O of 2n. Got it? Because this isn't happening every time. It will be like 0, 0, 0, 0, or maybe it will be like 1, 1. So it's like 1 iteration, 2 iteration, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe 0 again, 14, maybe 15, and then 16, 17. This is how the iterations goes. Thereby, 2n at the worst case. Because this pointer will go here. This pointer, the worst case, can go here. That's why 2n. What about the space complexity? No extra space. So a big O of 1. That's what the optimal solution will be. And if you tell this entirely to the interviewer, he will be super duper impressed. So coming back to the sheet, I can say that these couple of problems are done. With this, I'll be completing the step 3.1 and you can try this problem. Number of subarrays. This was the longest. You can try finding the number of subarrays with a sum k. So again, hashing will be used in the optimal solution. Give it a thought. We will definitely be solving this in the upcoming days, but till then, you can probably take this as an assignment. So with this, I'll be wrapping up this video. I hope you have understood everything. So to continue our tradition, do comment understood beneath the video because that is the only thing that motivates me, that you guys are understanding everything. And yes, if you haven't followed me on Instagram, Twitter, LinkedIn, all the links will be in the description. And if you are new to our channel, what are you waiting for? Do hit that subscribe button. And yes, so with this, let's wrap up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken, don't ever forget you're golden.